were teleporting. On the one hand, this experiment, which I will tell you about, it raised a lot of interest because there are millions of atoms there. And people always thought that it's only like, you know, a single particle that is really quantum. Big objects cannot really be quantum. And here we demonstrated that we can do quantum teleportation on millions of atoms. So that was a big deal. But on the other hand, we only teleported one pair of those unobservable variables. And if there are 10 to the 12 particles, there are at least 3 times 10 to the 12 of those degrees of freedom. So this is already way ahead the answer to the question, can we teleport a human being? How much information do we need to learn about ourselves as compared to a single atom? Infinite. So, I don't think so. Still, one other thing I want you to understand, like what exactly we're teleporting. So, I told you that every little spin, every atom, every magnetic moment of the atom can be either spin up or spin down on a superposition. And imagine that those atoms which are flying there, by some means, I oriented all of them along one direction, along direction X. I can do it by shining light on them. But then, complementarity tells me that if I know the direction of this spin along X, then its orientation along Y or Z is completely random. Now you will ask me, wait, if this spin is oriented along the x-axis, there is no projection on the Z or Y, right? If my hand is oriented this way, it doesn't look that way or this way, it looks this way. Quantum particles are not built that way. Whatever you do with this spin, it will always point either in one direction or the other. So it's like this quantum coin. In whatever direction I project it, it will always be this way or that way. So if my spin is oriented this way, and I want to measure its projection on this axis, I will either have plus or minus, up or down. That's this unpredictability, intrinsic. And now a little bit of, you know, let's kind of train our brain muscles. If you have this spin, which can be up and down. So it's like a coin, which I flip, and it can be up or down. And I have many of them. What would be the sum of projections on this direction? And it's like, it's flipping a coin. When you go to a casino, and, well, you don't go to a casino, but let's imagine that there is a fair casino without any bias and stuff. Then, you know, you press the button, you get plus or minus. And you press it 1,000 times, what would be the result? The result will be 500 pluses, 500 minuses, but not exactly. There will be some uncertainty. And this uncertainty will be equal roughly to a square root of the number you try. So if you flip a coin 1,000 times, I invite you to do that. And count how many heads you had, how many tails you had. You should get approximately 500 of each, plus minus a square root of 1,000, which is about 30. So you try once, you will get maybe 460 of heads and 540 of tails. You try again, you'll get maybe, you know, 490, 510, so something like that. Which actually reminds me when our unfortunate President George W. Bush was elected last time. He was elected with the vote margin, which was much, much less than the square root of the number of voters. And I'm asking everybody, how is that possible? In physics, such things are only possible when you have a feedback. Otherwise, you cannot get what we call a sub-Poissonian distribution. Yeah. Let me just see where we're. Okay, well, we're coming to the end of the time, and I haven't even started. But so I just told you that if all those spins are oriented along x-axis, then if I want to measure the projection on, for example, the vertical axis, I will have the uncertainty, which will be about the square root of the number of those particles. So I can plot this thing here, and I will get some distribution. And in here, this will mean that the end of this vector is uncertain. So if I have 10 to the 12 particles, the uncertainty will be a square root of that, which is 1,000,000, 10 to the 6. So the angular uncertainty will be 1 over 1,000,000. It's a small angle, but we're measuring much smaller things. So in my system here, of all those flying spins, with all my best doing, I cannot know the direction of this collective atomic spin better than 1 over 1,000,000. And I want to encode my information in the direction of the spin, and then teleport it. Yeah. Okay, I think we'll need 45 more minutes. I'm sure you agree. Let's see where we can cut corners. No, this I want to tell. So, some years ago, this is the argument that brought Einstein to the conclusion that quantum mechanics is fishy. Because he said, let's take two particles, and let's put them, you know, one in another galaxy and one here. Each of them has a position and momentum. Quantum mechanics does not forbid me to make those particles in such a way that I know the distance between them exactly, and I know that they travel with exactly the same velocities in opposite directions. Think of a grenade, and it's just blown into two pieces, and those two projectiles are moving. You can believe me that they are moving with exactly the same velocities if they're the same in different directions. So, long story short, you are allowed by quantum mechanics to know exactly the difference between the two positions and the sum of the two momenta, the two velocities. Now, this state is called an entangled state, and the argument of Einstein, Podolsky, and Rosen was the following. I sit on planet Earth. You have the particle in another galaxy. I can decide here, I want to measure the position of my particle. As soon as I measure the position of my particle, I know exactly the position of your particle, which is millions of light years away. But on the other hand, I can decide to measure the velocity of the particle that I have. And because I know exactly the sum of the two velocities, I will immediately know the velocity of the particle that you have. So, by my free will, I can change the reality, which is millions light years away. Einstein could not tolerate that because he knew that there is relativity theory which prohibits anything to travel faster than light. And here I, by my free will, can actually decide whether the particle in the other galaxy will have the known position or the known velocity. Turns out that there is no immediate contradiction with relativity, because I am not transferring any information by this process. It's like I look at my coin and I see tails, and then I know that if you look at it, you will also see tails. It's a correlation that we're establishing. We're not sending any signals. But at any rate, those two particles, for which you know the difference of the positions and the sum of the velocities, they were called entangled. And my big spins that I just told you about, they can be made entangled as well. And this entanglement is the backbone of teleportation. So, in a nutshell, the teleportation works in the following way. You, in this other galaxy, or in my experiment, half a meter away on the optical table, and I, we share two entangled objects. Then I take a third object, and I perform some operations, and as a result, the state of my third object is transformed onto the state of your object that you had there. I'll show you a cartoon. No time for that. Sorry, no time. Yeah. So this is just, to show you that we really do some experiments. So this is the close-up at the cell which contains all those flying atomic spins, and this is another picture of another cell. So it's the atoms in this cell, you cannot see them, I'm sorry, but it's a very special cell, and we teleport the quantum state, or the direction, in other words, of the macroscopic spin from one cell to another. Yeah. Just to give you an idea of what an entangled state of those two giant spins is. It's very simple geometrically. I told you that if I have this oriented spin, then I will not know exactly its direction, right? I will only know its direction to 1 over square root of n, like 1 part in a million if I have 10 to the 12 particles. If I have 100 particles, it's only 1 over 10. So the angle becomes bigger when I have less particles. This is the manifestation of quantum effects being stronger and stronger as you go to smaller and smaller systems. So I don't know the direction of this spin, and I don't know the direction of this spin. But if I make them entangled, they will be in the superposition of all parallel directions. So I don't know the direction of that one, and I don't know the direction of this one. But I made them such that if I measure the direction of that one, I know the direction of this one. So this is entanglement. This is correlations beyond the quantum limits, so to say, beyond the limits of the measurement. Yeah. And now, what is teleported? Imagine that I have this giant spin, and now I look at this. So this is like part of a planet around the North Pole. And I'm looking at this thing from the top. And imagine that I can have this direction with its uncertainty, or I have another direction with its uncertainty. If I choose to encode my information in the direction of this spin, clearly I cannot put as much information there as I wish, right? Because I cannot tell this from that. This is the uncertainty, this is the uncertainty, they overlap. So I can use this kind of dense coding in such a way that I cannot tell the difference between those three states, and yet I can teleport them using the entanglement on the other system. So it's a little glimpse of how quantum teleportation can be used for information transfer. Suppose you want to encode some secret message. And you take the secret message and you encode it in the direction of the spin. And then you make it such that it's encoded so densely that you cannot really tell the difference. And then the enemy cannot read it because, there is no way to read. But then you teleport it on the other side, and on the other side you have exactly the same information, and then you can choose to decide what to do with it. Yeah, so there are philosophical issues, we can discuss them later. Back to the same thing. And so So here is the teleportation principle in a nutshell. This is really like, I'd say, the 4th year arithmetics, not even mathematics. So all we need to figure out is that if A plus B equals to C, then A equals to C minus B. And I hope that we will all make an effort here and now and try to get it. By the way, this talk is dedicated to our 2 people whose birthday today is celebrated. So let's give them a big round of applause. Good. So, refreshed, invigorated, the principle of teleportation. I am on the planet Earth, you're in another galaxy or another room or whatnot, and we share 2 entangled objects. And entanglement, in this case, is written here. And it doesn't even have to be the position and the momentum. It's just a pair of some variables, for example, the spin projections, that I cannot measure simultaneously. Any pair. But I created those 2 objects in an entangled state so that x1 minus x2 is known and p1 plus p2 is known. I know that I created them in this state. I don't know x1, I don't know x2. Separately, I don't know p1 and p2, but I know that they're correlated. I created the entangled state. And now I take the 3rd object. And I want to teleport those 2 variables onto here. And again, I have no way to measure this one and that one. I cannot measure them simultaneously. And now watch my hands. So what I do is I take this entangled object and the object that I want to teleport, and I measure the difference between those 2 and the sum of those 2. And I'm allowed by quantum mechanics to measure the sum and the difference, because for those who remember quantum mechanics, they commute. I cannot measure them independently, but I can measure the sum and the difference. And now I got some numbers here, and those numbers I can write down. In the process of this measurement, I have destroyed the quantum state of both of those things. So if you wish to be teleported, you better make sure that the process works. Because the original is destroyed, I'm sorry. And what about the reconstruction? Well, the reconstruction goes in the following way. I take those 2 numbers and I send them here. And I tell this guy, take your x1 and displace it by this number. And take p1 and displace it by this number. So let's look at it carefully. x1 is actually equal to x2. So if I take x2 and subtract this cx, which is x1 minus xv, right? I take this and I subtract it from that. x1 and x2, they cancel out. What I get is xv. Does it make sense? Thank you. So this signal cannot travel faster than light. This is something I have to tell over the phone or send with the radio waves or do whatever. This is an absolutely classical piece of information. This piece of information contains no knowledge about the state of my object. It only contains knowledge about correlations. So I am doing teleportation, which is like the disembodied transfer. I first established the quantum link, which is entanglement, and then I did some black magic and sent some numbers, and then I did operations here, and as a result, as I told you, this thing became xv and this thing became pv. So I teleported the xv and pv from here to here without, yes please.
Do you destroy the one on the right side when you
Well, I change it in a predictable way. In principle, I can go back. This is reversible information. This is irreversible information operation. So yes, but unfortunately, you know, if I reverse this operation, then I will be left with empty hands because I destroyed the original and I don't have the copy. Okay? So with this, I will just show you. Yeah, so this is what we've done some years ago. And because of this wonderful word quantum teleportation, and of course because we are so wonderful physicists, we got on the front page of CNN. This was really funny because all other 9 entries on this front page were about killing, raping, bankruptcies, fighting, wars. Just before my lecture, I discussed it with a couple of people. And I claim here, open and loud, we live those lives so that we can...
Transported.
Say it again?
Transported.
Transported. No, we live those lives because we want to express ourselves as best as we can. We want to fulfill our abilities as well as we can. And this doesn't work without striving for excellence, right? So now I'm being pedagogical, you know, a father of the children and so on and so forth. But what I'm saying is that I believe that if a lot of people do science or arts or something that requires serious thinking, there will be much less wars in this world. Yeah. Right, so more bragging. Okay, so this is the latest experiment where we actually succeeded in teleporting a big spin state from this station to this station. And you know, so you have, you know, those little bits and pieces here, and this is maybe 10% of what is actually on this other part of the optical table. But what you do is you send light. So, yeah, you do some tricks with magnetic field. You send light here, it goes here, it goes here, and there it's detected. So light transmitted through, get those 2 guys entangled. And then I make a measurement. And remember, I told you that I have to make a measurement, and then I have to send the results to another station. And I'll send the results to here, and here I do something with those spins. And the result, I have a teleportation. And I don't want to bother you with the experimental data graphs and stuff like that. Trust me that this operation has been done in a way that is impossible without using quantum entanglement. And this is why it's called quantum teleportation. This is why people are interested in it. Because we have transmitted something that you cannot measure and transfer by simply writing it down or dialing it on your computer. You require quantum entanglement for that, and this is fun. Yeah. Yeah, we have to go, more discussions. Yeah, so this is what I just said, that, you know, it wouldn't send a person, rather it would destroy a person at point, make a copy of him or her at point B, and the fidelity is not 100%, so, you know, I wouldn't like you to be a volunteer. Yeah, well, we can discuss this later. I want to show you a wonderful group of people. So this is how all that is done. With a lot of fun, and as you know, this is a typical day in Denmark, probably November, January. Anyway, thank you for your attention.
We have time now for a couple of questions, so if you have some questions, just raise your arm. There's one over there.
Hello. with all this uncertainty with the particles, how do you know that it works?
That's a very good question. So in quantum mechanics, I only can tell probabilities. So, for example, I can tell that, if I encode my spin with a certain orientation, and then I measure 1,000 times, I prepare it and I measure, I prepare it and I measure. With 30% probability I get that, with 70% probability I get that. This means that I know my state. And then I do teleportation and I measure 1,000 times on the other end, and I see that I get the same statistics. So this is where it's really kind of fun. You cannot tell much from a single measurement. Statistics. Yeah.
Any other question? No questions? One question.
Hi. Do you need a direct light source to entangle two states? Okay.
Yes, so this is, we didn't have time, but indeed, entanglement always involves interaction. So when I showed you this little picture, no, I'm going the wrong way. Yeah, so here we have those two cells and we send light through them and we make a measurement, and this light going through interacts first with that one and that with this one, and this is what provides the entanglement mechanism. There is a strong and fundamental statement that if two systems do not interact, you cannot create entanglement. So you cannot create entanglement by local operations only.
There's another question here.
Hi, the two-split experiment, if it's so unstable that the photons can disappear and enter in totally another place.
I can see you. Where are you?
Yeah.
Oh,
So if you're watching this step, will it destroy this experiment, or is it only when you don't watch this it works?
Okay, so I have two slits, and I am sending photons from this source, and I am looking at the interference picture there. I sent one photon, it hit the screen somewhere. It's pretty random. I sent 1,000 photons, and then they will hit here, 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 but not in between. If now I sit near one cell, or I put a little detector, and I want to absolutely unobtrusively, just to see which path the photon took. If I know exactly which path each photon took, there will be no interference picture. They will go there. I am not destroying photons. There are ways in physics to observe which slit the photon went without actually absorbing this photon. And it's actually, there is a simple way to explain it. Think of a photon as a particle and also as a wave. A wave always has a phase. A phase is like, where is the maximum, where is the minimum. If I see which path the photon took, I destroy its phase. I give a jolt to the phase, which is random. And if I have two waves, and one of them has a randomly changing phase, I will not have interference. So that's how it works. It's a dualism between good and evil.
Okay, now we'll take a break of 5 minutes. You can ask questions to Eugene at the bar as much as you want. Do whatever you want with him. And I want to say that the cycle runs every second week. The next, in 2 weeks, Tuesday, we'll have English physicist called Rupert Sheldrake. He's a very famous biologist and author of many books. And his theme of research, his topic of research, is this thing called morphogenetic fields. So fields of knowledge between similar species. And maybe, I don't know, how does he explain, but maybe you have to explain through teleportation, because no one has any idea how it would work. So I hope you enjoyed, and please stick around for the concert. Thanks.